In this video lesson, we are going to study how a quadratic function can be applied into the modeling business problem. Let's now look into our first example here. And so before worrying about whatever being written here in question A, let's read and find out what information we are given with. And so the market research department of a company predicts that the demand equation for their product, whatever product that is given by, so what we have here is a demand equation. And notice for now, the demand equation is expressed as P for the price being a function in terms of Q for quantity. And so some brief explanation of what Q and P represents. The first question now is asking, find R of P. So a function capital R, we name that R of P to represent the revenue. So we're looking for R of P. So this functional notation is intending that your function R here is now going to need to be dependent on the P variable, which is the pricing, relating back to this demand problem right here. Then P is the pricing. And so revenue is intended to be a function of pricing. All right, so into my writing board here. So once again, revenue, there's only one permanent rule. Revenue equals the price per unit being sold times the quantity. And anytime you are doing a business modeling problem right there, you constantly have to remind yourself this rule of revenue. And so in this context, and that makes perfect sense now that we can name our revenue as a function capital R here. But so in the way how it looks right now, consequently, price is the P variable, lowercase p, and quantity is the lowercase q variable. And so straight out from that fundamental understanding of revenue, then R as capital R to represent revenue must equals P times Q. And so remind yourself that the intention of this question is to express our revenue R as a function completely depending on the variable P. However, if we're looking back into our currently setup for the revenue, then it already had some P variable, but the other variable is a Q variable being involved there. So we still need to find a way to work this Q variable and find a way to substitute that with some other known expression in terms of P. And that's how we're done. And so we are given, and look back into our problem right here at my yellow highlighted area here, but we already had a demand equation given as P equals negative 0.5 Q plus 160. So unfortunately, so we have the demand, and this is the traditional way of how we write a demand equation, P as a function, price as a function of Q. But unfortunately, remind yourself that we need to write our function R here in terms of as a function of P. So if we're substituting directly this into our P times Q, then we can only substitute this negative 0.5 Q plus 160 in place of the P variable, which is not what we're looking at. And so here in that case, along with what I'm explaining, allow me to rewrite our demand equation in a cleaner version. So P equals negative 0.5 Q plus 160. So I had a different video lesson detailing how to rearrange an equation like this to become an equation, same equation, but to express Q, the variable Q, as a function of P. And so you can find that other video lesson of mine to find out the detailed steps for here. But algebraically, this equation now, the same demand equation, we can re-express that as Q equals minus 2P plus 320. And so now, logically, now we can substitute this expression minus 2P plus 320 into our Q variable of the revenue function. And so now let's see how it can be done here. So now our revenue, originally P times Q, but now knowing that Q has an expression in terms of P being minus 2P plus 320. So now we can represent Q by that expression of P and substitute that into our revenue function for Q. And so now our revenue function is in turn becomes P times minus 2P plus 320. You can now just simply distribute that common factor lowercase p into each term here, and we consequently come out with minus 2p squared plus 320p. And so this final expression of ours right here is simply our function, our revenue function, as a function of p. R of p now equals minus 2p squared plus 320p. And now here we come to our next question of the same example. Demand equation, P equals negative 0.5Q plus 160. And throughout our work back in part A, then we successfully re-expressed this equation as a function Q in terms of P. And so the question here in part B is asking at what price P should the company sell each unit to get the largest monthly revenue. And so looking back into the answer we've had back in question A, then we already finalized our revenue as a function of P. We came to that answer, and then that was equals to minus 2p squared plus 320p. But indeed, as a matter of fact, if we're looking further into this function, then what we look at here, what we came up here is a quadratic function of the variable p. So R is a quadratic function in terms of the variable p. And so in that way, I need to remind everybody that in terms of the formal quadratic language, then the quadratic term has coefficient negative 2, and the linear term has value 320. So that's the value for the linear coefficient. And so immediately finding out that the quadratic coefficient is being a negative, then think about if we're putting up the graph of this quadratic function R of p right here, then we are expecting a quadratic having a parabola pointing down like this, where the vertex will be the maximum value. So the vertex is the highest point on the graph, which makes perfect sense with this question right here. And the question now is becoming clear at which price. So in this problem here, in our applying context here, then we're going to put the p variable on the horizontal axis and the r variable on the vertical axis as the output of the function. And so the question here is asking at what price of p, at what price p that we're going to reach the largest revenue value or the largest vertical value right here. So first thing, we're finding out how big p is. And so now, immediately realizing that our function now is a quadratic function, then finding that p value, finding that price value that gives the vertex is going to be simply minus b over 2a. And that brings us into, after substituting in the values, minus, in parentheses, 320 divided by 2 times negative 2. And that comes out, after calculation, being 80. And we actually found our answer. So we found that P equals 80. But formally concluding in the business context like this, our final conclusion say the company should sell $80 each unit to get the largest monthly revenue. And that's our conclusion right here. Or in short, price should be $80. And let's now advance to our last question. What is the largest monthly revenue? What is the largest monthly revenue? And so now you can see that it has a certain order of work here, but once we found out at which price we should be selling to make the largest revenue, and keep in mind that at the end of question B, we did not find out how big of the revenue we can make. But now this question here, we're going to answer that. So the largest monthly revenue in the context, in the way how your function here being recognized as a quadratic, then to find the maximum. The maximum revenue is to be found by simply substituting that P equals 80 into your revenue function. Because we already knew from question B that at this price and only at this price, the company is going to maximize, is going to max out their revenue. And so now it's just a matter of substituting in and evaluate your function at P equals 80. So now I'm going to have minus 2 times 80 in parentheses square plus 320 times 80. And final value comes out being monthly, it's our maximum revenue here is $12,800 monthly for revenue, or R equals 12,800. And then as an interpretation, then the largest monthly revenue is $12,800 monthly. And so here we are at the end of example 1 here, and before I'm gonna completely close that down, I just need to give some explanation, some interpretation in the concept of the entire problem here. But just think about how we are leading a market, how we're running a business right there. Then, of course, price, the reason there's the whole intention why we need to sometimes express the revenue in terms of price right there. Because admittedly that we tend to express price as a function that depends on quantity. But somebody else can argue that normally we adjust our price to attract different numbers of customers who buy our products. And so that's the reason why sometimes in this problem we have to write our equation here as quantity, or representing the number of customers that buy our products here is to be a function that based on how we adjust our price. So that's how we got negative 2p plus 360 way back in our development of question A answer. And so now, so once again, this thing here I'm saying now that's a lot of time we need to adjust P to attract our to come up with different number of customers. So our price here going to attract customers differently. And with different adjustment of our price right there, it leads to, consequently, our revenue is going to, it makes sense to be dependent on the price right there. And that's how we came up with negative 2p squared plus, and I noticed I had a typo here, but it's 320 actually. So minus 2p squared plus 320p right here. So once again, as we keep adjusting our price right here, then we're gonna gain, or we're gonna earn different revenues. We're gonna make different revenue values. And so at the end of question C and B right there, then we are going to hit our largest monthly revenue. So when we adjust to price equals $80 a unit right there, then we can sell at our best. We can make our best revenue being $12,800 monthly. And so that's a way to interpret these results right here. All right, and let's get ourselves into example 2, showing us how to model a business problem using a quadratic function. And this problem, I designed this problem to make it a little more challenging, so that you can. But after looking through, you're gonna see all of that concept in business all being circulated around in this one particular problem. So, analysis of a manufacturing company shows that as the demand of their new product, 82 units can be sold daily if the price is set at $18 per unit, and only 80 units can be sold daily if the price is $23 per unit. Analysis also shows that quantity sold daily Q and price per unit sold P have a linear relationship. This information here is important. So let me go ahead and highlight that. So right here at the end of the problem description, right here at the end of the information description, then we had we know that we're looking at the demand. So what we know here is we are provided with a demand right here, okay, as the demand of their new product. So this relationship here is our demand. So our first question being brought up into this example here is that find the price per unit P that maximizes the daily revenue. And so before I get too far into finding a way to answer this question part A right here, let's have a look and let's just simply summarize down, make a small summary of the given information. So when price being sold at $18 per unit, then we can sell, that's why Q equals 82 units. We can sell 82 units daily when price is being set at $18 per unit. And then it's just the way how the business runs out there. We adjusting prices. Sometimes we want to push our price up to learn the market on our products right there, or sometimes we might want to adjust by bringing it down. So when we change the price to a higher price here in this problem, actually it's $23, then the quantity being sold daily reduces down to 80. But basically, let's not be too worried about reducing or the increasing. But what I see now is that we have adjustment in price right here, and that also caused adjustment in quantity being sold right here. And so now, at the end, sooner or later, we're gonna have to run into creating our demand function, coming up with our demand function, because here, so now let's look a little further into the question, but we want to find the daily revenue, and the daily revenue here, as in a far picture ahead of time, once again, the only rule of thumb that we have to nail down, revenue equals price times quantity Q right here, and allow me to start using shorthand notation here. And so, but then the further intention is that now I'm going to highlight this I want to find the price per unit P that maximizes the daily revenue. The part where I highlighted right here is actually points out the intention that we want to ultimately write our revenue function as R in terms of P. So we want to regard P as the independent variable, and then R is the variable that depends on P right here. So how does that lead us into deriving our demand function? So the tricky part here is that demand here is simply being given as two different pairs of value. When price equals $18, then you can sell 82 units daily. When price changes to $23 per unit, then you can sell only the $80. I mean 80 units daily. So, and I have expressed my I have given an explanation in other video lessons, but demand or supply can always be written in two different forms of equation. You can either write your demand as P equals some M Q plus B, or you can also write the same demand equation, but you can also write your demand equation as Q equals some other slope, capital M P plus B. It all depends on what we need right here. And in this problem, we really are starting from completely from scratch. And so which one should we choose in this case right here? So you can see now that making that connection with our goal earlier, we want our final revenue function to be in terms of P. And any revenue is already P times Q. So that means I want to find a way to substitute this Q with some expression involving P. So in that way of arguing, then I need to be able to derive my demand equation as a function Q in terms of the P variables. And that's the reason for why the reason why I created that other videos detailing the steps how you can from your given information and be able to create any of these forms of your demand equation depending on the situation that you need with them. And so once again, allow me to put this aside, even though I keep bringing it up, and I have to erase it because eventually we will come back to that. But let's for now derive our demand equation. And so now we know that we need to have our demand equation expressed Q as a function in terms of P. And I should have also mentioned, why do I know to set up in a general form a slope times the variable plus B? Because we did have that other piece of information where I highlighted in yellow here, saying that, you see, analysis also shows that quantity sold daily and price per unit sold have a linear relationship. And that's the reason why I can simply choose this starting form of my equation right there. And the rest is simply just a matter of finding out how big our slope value is and how big our y-intercept value is. And so, in this case, our slope for the demand equation, capital M, equals, I'm going to go with Q2 minus Q1 over P2 minus P1. And so really you can, out of these two pairs, you can choose whichever pair here, being P2 Q2 or the P1 Q1. Make sure they just go in pair. That's all it needs right there. So how about I'm going to call this P2 and this is Q2 correspondingly. And then this is P1 and this is Q1. But really you can just rename them the other way around. You can call this P2 Q2 and this one is being P1 Q1. It's all your choice. But the formula here is, make sure it's in this order right here. Q2 minus Q1 divided by P2 minus P1 for whoever you call P2 P1, P2 Q2 and P1 Q1. And so now into my equation here, then the slope here is going to be 80 as a calculation setup right here, 80 minus 82 divided by 23 minus 18. And so final calculation comes out being negative 0.4. And so now our demand equation is halfway done. Q equals to negative 0.4 times P plus some y-intercept value. And so the next step now is just to find out what the y-intercept value is. And once again, I'm going to just simply substitute in any one of my preferred choice indicating a pair of values here. I can use P1 Q1 or P2 Q2. So I can just simply go with P2 Q2. So Q2 equals 80. So I'm substituting 80 into my left-hand side, equals negative 0.4 times P, but P2 correspondingly was 23 plus B. And so now, solving for this equation, we come up with, and allow me to start to skip a couple of small steps right here, because I had separate videos just showing you how, in details, how we can do all these things in every algebraic steps like that. So make sure you find my other videos in case you are still feeling unsure about how I move on with these little steps. But so now calculation turns out that my B value must be 89.2. And so now our demand equation is ready. Q equals negative 0.4 P plus 89.2. And now we are just ready to nail down our revenue function. So I have to make clear with everybody that all our work to derive the demand equation in this problem, Q equals negative 0.4 P plus 89.2, all that work there was a requirement before you can actually answer this question in part A, find the price per unit that maximizes the daily revenue. And so now revenue, back to revenue, always equals P times Q, price per unit times quantity that you can sell. But now, according to our demand equation, then Q can be expressed as a function of P, negative 0.4 P plus 89.2. And so now we can just directly substitute, because P is already here, so I'm keeping it the same, but Q can be substituted by negative 0.4 P plus 89.2. And now our function, it just simply going to take another distribution step right here, but I'm going to distribute that common P variable into each of my terms here. So first term is going to become minus 0.4 P squared plus, next term here is giving me an 89.2 P, and this function we have here is our function. Now we are finally at our function revenue here being expressed as a function in terms of P right here. And having that function being expressed in terms of P, it makes perfect sense with the fact that the question is looking for find the price per unit, so which value of P that maximizes the daily revenue. And so now, by the way, the function we have here now is and allow me to just now only show my final revenue function, because we are ready to answer our question in part A right here. All that work we've done is just to start with question A right here. But so what we have here is a quadratic. And so you can, as the more example I'm showing you, the more you can see that quadratic functions has a tremendous amount of applications out there in business work. So this is a quadratic function. The quadratic coefficient is a negative 0.4, and the linear coefficient is 89.2. And immediately recognizing that the quadratic coefficient has a negative sign or being a negative value, then we can immediately have that expectation even before we solve the problem. We have that expectation that the quadratic or the parabola here is going to have to be a pointing down parabola. And so the vertex in our problem will become the maximum. So the vertex is here, which is also, in this case, also the maximum value. And so that's why connecting with the worded question here, we're looking for which value at, so here in this problem, we're putting the P variable on the horizontal axis, and the output value of your revenue is on the vertical axis, corresponding to the Y value. And so at which P value, P should be equal to which value that produce our maximum value for revenue. And so now we are ready to apply our finding maximum or minimum value skill for a quadratic function. So all it needs here is the maximum can only happen in any quadratic function. In any quadratic function, the maximum can only happen at P equals minus B over 2A. And so after setting up the formula, then the substitution can just simply come in and minus 89.2 over 2 times A substituted by negative 0.4, which in turn calculation comes out being positive $111.5. And so now we can be saying that, so making our general final conclusion here, revenue is maximized at, or is maximized when the price that company sets to be $111.50. And so that's how we answer a question in part A. And once again, keep in mind for yourself, and we are doing business, so we have to pay attention to every single detail here. But all we answer here is at which price giving us the best revenue, giving us the maximized revenue. So in other words, we did not find the answer how big, how large our revenue, our daily revenue can be yet. And that's the whole reason we're going to bring ourselves into the next question. All right, so here we go. This is our question part B of the same exact example over here. All that highlighted area is still here, but that's just the information of the problem. But now the actual question here, we find the daily maximum, find the maximum daily revenue. And so in our context here, then the wording of the problem is intending to find how high our revenue value can hit, or the graphically vertical value of our parabola here when we are at P equals 1101 when we are at 111.5. And so now to find that maximum value, all we do is just simply calculate or at 111.5. And so which in turn substituted into our quadratic function that we found previously, then negative 0.4 times 111.5 all square plus 89.2 times 111.5 and calculation now shows me that maximum daily revenue turns out to be $4,972.90, to be clear. And so as a final conclusion, as a formal conclusion, we can say that at selling at price $111.5 per unit, our maximum revenue, and indeed our daily Maximum revenue is $4,972.90.